we're super excited to have this in recording in progress. So, but we're very excited as well to have Dr. Jing Gao speak to us today as part of the Project WiCCED seminar series. I'm going to introduce her here shortly, but wanted to just take a moment to talk about Project WiCCED via a short film that was developed over the winter for AGU TV. There's a long version. I'll show you the short version, 1 minute. And so we're going to just play that, and then I'll do the introduction. So again, welcome. I'm happy to have people here today.
Project WiCCED has a fun name. It stands for Water in the Changing Coastal Environment of Delaware. And one of the things that I love about the name Project WiCCED is it talks about the challenges of water given the changes that we're seeing.
When we look at the whole WiCCED groups, it is complete diversity, complete inclusion. It's like amazing. Every sector that you can imagine in Delaware is part of it.
We're lucky in Delaware because it's a small state, and so we can develop strong relationships between academic institutions, between communities, the government, the private sector, et cetera. If we communicate with each other, then we're able to identify the needs of the state and the communities.
Models created here in the state of Delaware can ultimately impact our region, our nation, and ultimately the world.
Well, great. Well, that's many thanks to Ann Alvarado for her work on that, and Amy Slocum, along with our distinguished speakers of Holly and Goulney there. Again, there's a 5-minute video that's even more in depth and showcases a lot more of our research that's available on our website, projectwicked.org. And so check that out. Feel free to reuse it. We also have the B-rolls and stuff if you want to cut it in a different way and make it highlight your research better. I'm thrilled today to talk about Jing Gao. She's one of the faculty members that we were able to really bring on to Project WiCCED early on. She joined the University of Delaware at the same time Project WiCCED was launched, and her skills and skill set was just perfect for this project. And if you haven't checked out her resume, you'll see that she's doing really amazing things right now with publications and things like climactic change and nature food, and a recent publication in Nature Communications that was listed as in the top 50 articles of 2020. So really outstanding scholarship, and also really fantastic grant work with National Science Foundation and others to really broaden the impact of data science and bringing forward a new generation of scholars. So we are very excited to have Jing as part of our project and working with us, and we look forward to her talk today. Just as a quick background for where she's at, she got her MS in remote sensing and GIS in Beijing at the Beijing Normal University, and then went to the University of Madison to continue that work, where she got her PhD as well. And we've been thrilled to have her at the University of Delaware for a couple of years now, and hopefully for many, many years to come. So Jing, I'll just stop talking and pass it on to the real expert, which is you. And thanks for being here today.
Thank you for the generous introduction, Kent. And thank you everyone for taking out some precious time of your day to spend with me. Do you guys see the slides in full screen mode?
Yes.
All right, cool. So today I'm going to talk about large-scale interactions between urbanization and climate change over the 21st century. So the key words here I want to emphasize on are large-scale and long-term. But essentially, my group's interested in examining interactions between population and climate over the 21st century. We're interested in large-scale interactions because climate is a large-scale phenomenon. So to truly understand how societies and climate interact, we must look at larger-scale patterns. We're also interested in long-term because climate is a long-term, climate change is a long-term process, and socioeconomic changes evolve alongside with that and also interact with it. And also because we we think some of the challenges that we see on the social side with climate change had to do with previously the long-term thinking had not been as strongly incorporated in our planning. Now to do this type of work, our choice of method is data science and machine learning. And I want to give a little bit more rationale for why that type of methods are particularly suitable. Now, the first reason is that socioeconomic processes change over space and time, different from physical and chemical laws that are spatially and temporally invariant. So data-driven methods, as the recent data revolution, increasingly we have more and more data with better quality. We're able to examine these new pools of information, and data-driven machine learning methods are good at identifying different trends and patterns and how they transition among each other. And also we want to say that the purpose of this type of modeling, the long-term large-scale spatial modeling of socioeconomic processes, is not to predict exactly what will happen globally in the far future, but rather to understand potential long-term large-scale effects of alternative societal trends. And we want to try this, use these type of methods also because in our work we've witnessed some limitations of conventional methods, which were primarily developed for capturing often small scale and short-term studies. So we hope to use these new methods, take advantage of new data to do a better job with long-term and large-scale research. Now today I want to share with you actually 3 different pieces of work. The first 2 are already completed. The last one is still ongoing. Now, so earlier I mentioned we're interested in examining how climate and population interact. Now, one element we haven't mentioned is in what type of built environment people reside in affects how population experiences climate change. But to model urban land at large scale for long term, it's still relatively new research direction. So first, I want to show some of our work in that on that topic, and then how urban land might affect climate conditions. Now, you might have seen many papers on this topic talking about especially urban heat island effects, creating more heat stress for urban areas. But many of these studies focus on, again, smaller scales, maybe individual cities, and shorter terms, maybe 20, 30 years rather than 100-year time horizon. So we want to look at the continental longer term patterns for urban land effects on climate conditions. And then we want to see how these altered climate conditions might affect populations' exposure to and experiences of some climate disasters. Now, first thing off, long-term large-scale urban land projections. This work has been completed. We examined 40 years of historical time series of spatial data, try to connect urban land development with characteristics of population and the physical environment. We examined 15 best available training data sets, modeled the world as 375 separate regions to capture local variations in the urbanization process, and generated essentially a global raster graded data set for where urban land might emerge over the 21st century with decadal updates. Initially modeled at 1/8 degree, that is about 14 kilometers at the equator, and then downscaled to 1 kilometer. As Kent mentioned earlier, this work was one of the top 50 paper in Earth Environmental and Planetary Sciences in 2020, and our data set has been downloaded thousands of times since then. And I want to tell you a little bit more about why this, what about these data sets are special, or essentially what we took advantage of the new data. And the first thing I want to talk about is we were able to capture the temporal evolvement of urbanization styles. So on the left, you're looking at conventionally how we model the total amount of urban land change over time. Is we contrast per capita, usually GDP, with per capita urban land, and treat the world as usually less than 20 regions, and each region has is portrayed as a point in the scatter plot, and then fit a linear model to it because of the limited amount of data. Now I ask you to mentally remove that linear line and think about the shape of that scatter plot. Now it probably does not look very linear. Now with the new data, we were able to examine. What we found is on the right, each dot corresponds to one country for 1 decade. Over the 40 decade we had data. We found that there are really 3 different stages of urbanization: rapidly urbanizing, steadily urbanizing, and urbanized. And then countries based on their urbanization maturity fall in these different clusters. And when they their urbanization proceeds over time, when they change urbanization styles, it goes directionally, in one direction, from rapidly urbanizing to steadily urbanizing, and eventually to urbanized. So based on this finding, we trained a modeling mechanism that can identify the urbanization style for each country for the next decade based on its recent past urbanization history. And this process can be iteratively run over 100-year time horizon, so that the evolution of urbanization styles for each country can be organically modeled under different scenario settings. Now here is an example for the country of China, how urbanization evolved over the 21st century under 5 different socioeconomic scenarios. And in the main part of the table, 2 means steadily urbanizing, 1 means urbanized. The country had already passed the rapidly urbanizing stage. So as you can see, by the end of the century, regardless of the scenario, the country will become urban, or what we call urbanized today. And in which time point over the century that transition happens depends on the scenario it is in. And these temporal evolution patterns we see are consistent with the storylines of these different socioeconomic scenarios. And they're organically modeled, so does not require arbitrary input from the analyst. Now another advancement we were able to incorporate by using data-driven method is we're able to capture local scale variations in urbanization styles. Now, as I mentioned earlier, previously when people model urban land change, usually they treat the world as less than 20 regions, lumping together different countries. But we know urbanization styles vary greatly even within the same country. If we think about the cities in the US, those on the East Coast, West Coast, and the Midwest, for example, have very different urbanization styles of their own. So here, examining the past, the patterns of the current cities, we were able to divide the world into 375 regions. and trained a flexible machine learning model for each of these regions. So you can think of it as we have a soft pile of clay that has no shape for each of these regions, and then we fill it into a mold. The mold was the recent past histories of the region's urbanization process. And these clay then took the shape of these different mold and then become different models. And we use these models to predict how urbanization will happen in these different regions over the next 100 years. So essentially, we have nearly 400 models running in parallel, making predictions, and then piece them together to have a global graded map of urbanization. So combining these two together, our modeling results are able to capture the temporal involvement of spatial patterns. Here I'm showing you an example. So you're looking at the northeast of the US, our region of the world. Each row is a different time point in the century, and each column is a different scenario. Now I want to draw your attention to the material intensive development scenario in 2060. That's the right row, the right column, the middle cell. And the business as usual scenario in 2100, that's the middle column, the bottom row. So in these two maps, as you can see, the total amount, this one and this one, the total amount of urban land in these two maps are quite similar, but the spatial patterns are different. And the spatial patterns they're showing reflect the storylines of the different scenarios. And once again, these patterns organically emerged from the modeling results and are not arbitrarily set. So another benefit we were able to harvest from having more data nowadays is we were able to conduct more extensive model evaluation. Without getting into too much detail today, we tested the model's statistical robustness, spatial and temporal generalizability, and were able to compare it with conventional models and see that among other advantages, especially having access to time series data, our model were better at predicting change in spatial patterns than previous models. So I want to show you some of the results. This is for North America. The small map at the top right corner is how much urban land there is in this region in the year of 2000. The two bigger maps at the bottom are how much urban land is projected for 2100 under a low urbanization scenario on the left and a high urbanization scenario on the right. Now overall for the US, we expect to see about 1.3 to 4 times the present day amount of urban land in this region. Now this might come as a surprise to see the high end of the how much urbanization might continue to happen. Yet this is a result of a pattern that has not been reported a lot in the past. That is, when we look at the past 40 years urban Earth observation data from remote sensing, we find that the total amount of urban expansion in the developed world and the developing world are actually quite comparable. Often we see higher change rate in the developing world, but that's primarily a result of smaller amount of existing urban land rather than actually more new development. So if this type of trend continues, a substantial amount of new urban land can be built in the developed world, and we will see many times of increase in this variable. I also want to mention that the model captured different urbanization styles in different parts of the world, in different parts of the country as a result of having those subnational small regions. So here is for Europe, similar patterns are seen. A substantial amount of new development is possible depending on socioeconomic trends. And this is Asia. In this part of the world, we expect to see about 2 times to 6 times the amount of present day amount of urban land expansion, and about 2 times to 6 times the amount of increase is also the global total ratio of increase we expect to see. Now here is Africa. Now Africa has reported the highest urbanization rate over recent past decades, and we expect that to continue. However, again, because its base number started as smaller, by the end of the century, the total amount of urban land in this continent might still be lower than many other places in the world. So now that we have urban land projected for the long term at larger scale, we want to see how that might affect climate conditions. Now, in order to do that, we examined 3 sets of scenarios. Now, the first for taking the continental US as an example, comparing climate conditions at the beginning of the century versus the end of the 21st century. Now, the first set of scenarios we examined is the current status quo. That is we consider only climate change, assuming that land cover, present day land cover will hold constant over the next 100 years. And we examined 2 socioeconomic scenarios. Regional rivalry is a scenario with low economic development. Its land change primarily comes from agriculture with low urbanization. Material intensive development is a high economic growth scenario. Its primary land use change is urban. So a lot more new urban development and mostly in urban sprawl format, but little agricultural land use change. And by comparing these 2 scenarios, we can also compare how much changes on climate conditions might result from land use change, urban changes versus agriculture changes. So here are changes over the 21st century in the average near surface temperature when we look at these different sets of scenarios for annual average temperature, summer and winter average temperature. Now here we examine percent change in mean precipitation again across the 3 sets of scenarios and the different seasons. Now to summarize these results, the key findings from this study is that urban land expansion could potentially cast a larger impact than agricultural land change on temperature and precipitation projections of climate conditions. Now this is an interesting finding because urban land covers a very small percentage of the Earth's land mass overall. And in the past, people usually have thought agricultural land, because it covers much larger land areas, would have a stronger impact on climate conditions. But what we found are different. And we found that urban expansion can double the temperature increase in urban areas averaged across the continental US. Double the temperature increase caused by greenhouse gas warming. Now that means if we ignore land use change, consider only climate change, we might underestimate the temperature increase by about half. Now for precipitation, we also find urban expansion having some effects. It would make rainfall events heavier and longer within urban areas while reduce precipitation in surrounding areas. It's as if urban areas are kind of like a sponge. It would soak moisture from its surrounding. Now this also has implications for urban vulnerabilities to heavy rainfalls and related other disasters such as urban flooding. Now that we see large-scale urbanization could actually generate mesoscale climate signals. Now, so it's not just local, but then how would this change come back to affect population experiences of extreme weather? Now we take population as exposure as the indicator of population experiences of climate change. And here we focus on weather extremes also as an indicator of population experience of climate change. Now again, we examine a few different sets of scenarios. Now first is when we consider only climate effects, no land use change, and then we overlay that with the present day population. So assuming no population change, to examine population exposure to future simulated weather extremes. Now the second set is we use climate simulations, consider only climate effects, no land use effects, but then overlay that with projected population, future population, incorporating population changes. This is the common practice of today's analysis. Now the last set of scenarios we analyze is climate conditions projected considering both climate change and land use change. And then overlay that with projected future population, so also reflecting population effects. And by comparing these different sets of scenarios, we're able to separate climate effects, population effects, and land use effects, primarily urban land use effects in this analysis on future population exposure to weather extremes. Now I want to explain a little bit more why I said primarily we focused on the urban land use for this set of analysis. So here we're looking at population change again under the two scenarios we analyzed in this line of research earlier. But because SSP3 is a low population change scenario, so very little effects can be detected using that scenario. So in this exposure analysis, we focused on the material intensive development scenario. Now we recognize high scenarios are not necessarily the most likely scenarios, but because it has a higher signal to noise ratio, it will make it easier for us to compare potential magnitudes of impact from climatic and socioeconomic changes. Now here we look at the total exposure across the continental US to hot days. Now in this figure, the effects of climate, population, and land change are captured as ratios, meaning if you see a number of 4, that means the effect would increase population exposure by 4 times. So the yellow bars showing across the entire continent how much effects we're able to see from these different factors. We see that climate has the strongest impact here, and then next the population. Land change seems to have a relatively small impact on the total exposure. However, when we break down the land areas by urban development density classes, the light gray is not developed, then low density development to medium to high development densities. We found that the amount of exposure in not developed area decreased, as what the negative numbers are showing. And the amount of exposure in developed areas, especially medium to high density development, increased by a lot. Now, what this means is, even though land use change did not, especially urban land change, did not increase the total amount of exposure by a very high factor, it changes at the individual level how people experiences weather extremes, and here particularly hot days. And to put this in numbers, I want to first draw your attention to this part of the table. So under different development density, how much exposure we see in the year of 2005 and 2090. So at the beginning of the century, most of the exposure to hot days we see are actually in the not developed area, 64%. But at the end of the century, 32% in low development, 42% in medium to high development density areas. So altogether, about 75% of the population will experience heat stress as urban residents rather than rural residents. And how does that affect at the per capita level people's exposure to hot days? So at the beginning of the century, the average, so per capita exposure to hot days across the continental US is 7 days per person per year. If we consider only climate change effects, in 2090, this number becomes 32 days per person per year. But if we consider both climate and socioeconomic factors, this becomes 41 days per person per year. So the socioeconomic change effects, even though smaller than climate effects, does matter. And also, this number varies greatly across different development density areas. In not developed areas, even at end of the century, it would be around 30 days per person per year. But in the highly developed areas, this would be 53 days per person per year. So altogether, we find that urban land use change, especially urban land use change, seems to have a relatively low impact on increasing the total exposure, but have a strong impact on how most individuals will experience weather extremes as important aspect of climate change. Now, that's our current work that I want to share, recent and current work that I want to share with you. I want to tell you a little bit about what future directions we're going into. One thing is we want to expand the analysis, examining population experiences of climate change while considering also land use change effects to a fuller and deeper extent. Now, the second is currently population and urban land are modeled considering each other's impact, but not closely integrated. While we know that this is active dynamic, so work will also be done trying to capture their interactions more, and in that way more realistically capture how land use change might respond to some of the climate impacts, and how population might move and react, considering how urban land and climate change might affect their experiences. So that's what I wanted to share with you today. With that, I thank you for your time and I welcome your questions.
Well, thank you, Jing. That was a great talk. Always a little depressing, but exciting as well to see about your work. People can feel free to throw in questions in chat or shout them out. I'll start off with a question.
I have. Okay.
Oh yeah, go ahead.
Okay. Hi, Jing. This is John.
Hi, John.
How are you? Actually, the question I had to ask you might have been something that you actually touched on in your future work. You mentioned there were like 15 drivers of urbanization based on our recent urbanization throughout the world. Which of those drivers do you think might change going into the future? Would per capita, would water resources, or some other drivers be different? And you have to change that relationship in your future models as opposed to the training data set.
Okay, yeah. Thank you for the question. First, I needed to clarify one thing is we examined 15 different data sets, but not exactly 15 different drivers. So some data sets are capturing the same thing, but we wanted to make sure that they're saying consistent things, kind of like triangulation of data quality. Some data sets provide more than one variable. I have to say that at the global scale, we were, even though we have more data now, much more now than before, it's still limited. The access to kind of drivers, like causal drivers through mechanisms are still very limited. So for example, for things like land tenure, we know it's influential for how land use changes, but there's really very difficult. First of all, it's difficult to quantify. Second of all, there's just no consistent information on that type of things across the world. So what we were able to do is we captured I think 8 driving variables we were able to get across the world, but then we used kind of spatial temporal heuristics that derived from remote sensing data as proxies for the drivers we were not able to have. So that model currently, what we have is it had some drivers, but it's still primarily an empirical model. So that's the data part and the kind of reality about the model. But I think I can still speak a little bit about what factors might affect how we react to climate change through urban land development. First of all, I want to say that even though in our results we show potentially large impacts and mostly kind of challenging impact from urbanization, but it doesn't have to be that way. So as I mentioned earlier, across different socioeconomic scenarios, we could see about 1.3 times to 4 times urban land development. So we can decide how much more we build. And also, more importantly, we can decide in what patterns we want to build. And I think there are many opportunities in this realm. That is, first, as cities grow and some smaller towns might emerge as new urban centers, we can build these new urban areas in more sustainable ways. And the second is many of our long existing cities, they're going to need renovations over the next 100 years. And these are also opportunities to change the land use patterns to more sustainable patterns. I think factors might affect the dynamic we see. First is quantity, second is pattern. So I do think existing literature has highlighted more of the challenging aspects of urbanization, but it really is an ongoing process that can be changed. I do think more research is needed decide. So, okay, if we build more, how much more is actually acceptable or crossing? If there's a threshold, if we pass that, it's going to be catastrophes. And then secondly, what spatial patterns could reduce some of these impacts?
Jing, I have a question, and that is to drill down into thinking about Delaware for a bit, right? If this relates to Project WiCCED and the coastal areas of our state, your maps were probably just have a hard time capturing the impact in a tiny spot like our state. But I wonder if you could comment on if you can drill down into something as small as a 3-county region or things like that, and what insights and implications that may have locally.
Yeah. So actually the finest resolution we've done with this type of work is at 1 kilometer. So we're with that we're actually able to capture some things in Delaware, and a graduate student of mine co-advised with Dina Varon to actually currently running that type of analysis. So at 1 kilometer, looking at centered around Delaware, but looking at the mid-Atlantic region to see how urban land change and climate change might interact to affect climate conditions. Some things you expect, such as warming, that's kind of unknown now. But I guess we can still try to examine to what magnitude and in what spatial patterns. And in that particular study, we also looked at wind resources, how that's going to change as we increasingly shift to more sustainable energy. But climate change, so wind spatial distributions and intensity of wind resources might change. And the wide sweeping urbanization, which is anticipated for the region, also changes the thermal and the surface properties, so could have an impact on how wind works. They wanted to see, we considering these two major changes in the environment and in the society, how different wind resources might distribute across the region. I would say we find some things that were surprising, but since that's still ongoing work, I'll hold on sharing too much details.
Jing, I have a question.
Yeah.
I thought this was a really interesting talk, especially, you mentioned, I think at the beginning that you want to move beyond smaller city scales and short 20 to 30 year time periods. And that's what I think of as really long and really big. So that's really interesting to me. But you also mentioned, I think I gathered from your talk that when you're talking about urban land use, that means to you maybe 3 different categories: a low density, medium density, or high density urban land use. Is that right?
Yeah.
Yeah. So, and you also mentioned, how, these are exploring potential scenarios, but, the future doesn't have to be this way. We could decide to develop differently. And I think one of the ways that I'm interested in that we could develop differently is by adopting more kind of lower impact practices, so that, say, a medium density urban land use might look differently than a medium density urban land use today. And so even though it might kind of fall into that same kind of coarse category of urban development, it might have a different impact on the climate and climate change. And I'm curious from your perspective, kind of how you might think about ways to account for that factor, the fact that maybe we would have more urban land, but it might have a different impact. Do you think there's ways to change that relationship between a medium density urban land use and the impact that it has on climate? Or would maybe expanding the types of urban land use classes we represent would be the way to go about that? Or how would you think about incorporating those impacts in those ways we might change our influence on the climate? Right.
So I think we are really trying to achieve the same goal, that is to create land use patterns that are sustainable, that has more resilience to climate disasters. I guess I think essentially the small scale type of work and the large scale type of work have to merge to get to the best answer. But I guess the point that I wanted to make is that see a type of urban land use pattern or arrangement that seems sustainable for say 20 years, but 100 years later or 50 years later may not be sustainable or resilient anymore, because the same land pattern, if climate changes, its interaction with climate would be different. So I think we need to extend our modeling skill to consider also longer term. So it's possible that something resilient for the next 20 years is the same for something that's going to be resilient, say, in 70 years. But it might also be that some of the things that would work for the next 20 years won't be resilient anymore in 70 years. And I think part of the reasons we see now is I feel like for some of the developments that we built, say, 20 years ago, it's not like they did not consider this at all. It's just they didn't consider maybe the magnitude of possible change over longer term. So what I'm trying to see is we should add this longer term thinking in our planning alongside with the shorter term consideration. And I do think there should be overlap between the short term and the long term interests, meaning there should be, I hope there will be urban land use patterns that will be resilient in 20 years as well as in 70 years. But we just won't know what those are unless we model them for longer term. And similarly, to expand for larger spatial scale as well, it's because places are not isolated. Not only they are receiving impacts from things like climate change as a very large scale impact stressor, but also many small places together could generate, as we already found, the mesoscale climate signal, so it feeds back as well, but not by individual city, but by all of them collectively. Does that answer your question a little bit?
Yeah, I think I agree with everything you're saying. So maybe I can follow up offline, but something I'm interested in is the potential for changes in the urban land use, adding green practices to affect the climate so that the regional impact of a city becomes different, even if we might classify it still as this same mix of medium or high density urban areas. The impact of that medium or high density urban areas might be different because it involves more, we've added these practices that locally change the way energy and water fluxes are moving around. And so how we might think about incorporating those management strategies into our predictions of what the future could look like, so we can better tune those management strategies and understand what impact they might have. But definitely agree with everything you're saying about the importance of thinking about this in those bigger ways as well.
Yeah. I want to follow up on that a little bit as well. I guess what I wanted to say is I agree with everything you're saying. I don't think we know that we don't. That's the next step of our research, is to see how these different patterns might impact, I guess, both climate conditions and people's experiences at larger scales on longer term. It's not there yet. I think it will happen. I don't have an answer for what type of patterns would be resilient at a larger scale yet, because we haven't run that simulation. But again, I think I fully agree that it's not just the amount of different density, but the spatial arrangement of them. What I wanted to see is the arrangement that might look sustainable in 20 years may not look sustainable in 70 years. So we have to do that analysis before we have conclusions.
Sure. Yeah, thank you.
Hey, Jing, thanks so much. This was a great talk. I guess kind of along those same lines, just following up with something that Carolyn was just saying, was I'm wondering if there is an indication. So on the heels of, well, what I'd like to think of the heels of COVID-19, thinking about migration patterns and thinking about changes of where people live and what the patterns are globally, and then even thinking about possible impacts on climate induced migration. Is there a thought that your urbanization model might change, and to what degree would that change? And I just, one quick follow up on that was just, is there a chance that the model can, the urbanization model can actually take in components of social breakdown so that we can start to see influences in those different regions that you have on how the countries or those regions deal with their social breakdown of possible impacted communities or impacted populations by climate change through the future?
Okay. Very, very different pathways of kind of I guess the uncertainties in the social economic process can be really wide. So we capture that with different social economic scenarios, usually not just by the numerical model alone, the spatial temporal model alone. So when we build these scenarios, usually they here we use the SSPs, which is a commonly used set of scenarios. They describe socioeconomic conditions in very different hypothesized world. And then we use that to set up the model and have the model run in its different hypothesized world to generate spatial patterns. So again, the model is not trying to produce exactly how the future will go, but rather under different conditions, how the world might look like. So I think they cover a really wide range of different things. So the reality hopefully falls within the wide range of uncertainty cone, but maybe not exactly any one of them, but it's within the range. So I guess that's how big social impacts are captured. So the COVID-19 impact, good question. We don't have data yet to say anything for sure. So anything I say from this point on is my own speculation, meaning don't hold me too accountable if they turn out to not be accurate. I think it is definitely a big shock to the system. However, for the type of work we're looking at long-term general trend. So this could be a big shock, but then gradually return to one of the general trend, the wide range of uncertainty scenarios still capture. And it could also shock the system to take a different pathway than what it was on before. But hopefully this new pathway is again still within the uncertainty cone that's different, the different scenarios we have would capture, meaning the shift of paths wouldn't change the qualitative conclusion, hopefully. Now, do we know which case is happening? Again, we don't have enough data yet. I think from the event alone, its impact on urbanization, some of the urban, I understand during COVID, some people moved away from cities. but urbanization, so the clustering of population, is a result of social and economic development. So as we gradually return to normal, that trend might return. Maybe to what extent, whether it would be at a discounted rate, I wouldn't know. The second is if it had shaped the economic system enough that we take a completely different path, I think that is maybe possible, but the current modeling of the economic systems for responses to COVID also have shown a really wide range. So it's inconclusive. Sorry, a very long answer for inconclusive.
Thank you. That's great. Thank you.
Okay, it looks like we're here at 11:58. So if someone has a last minute question, that's fine. But maybe we should actually just thank Jing with these last 2 minutes for an excellent talk and her work here. We really appreciate it. So thank you, Jing.
Thank you, everyone, for your time.